Okay, so first we'll pick some x inside of our compact set K. And then naturally, because K and C are disjoint, x is inside the complement of C. And because C is closed, its complement is open, and so it's inside the topology. Translation invariant says that we can shift a bunch of vectors, and if that original set is open, then the shifted version is also open. So C complement shifted by x is open, and 0 will be inside of C complement minus x. But our previous corollary said that if we had a neighborhood of 0, then we can find this symmetric subset, which was also a neighborhood of 0, such that u plus u is a subset of w. And for these individual u's, we can apply the same thing again. We can find a symmetric subset of u, such that v plus v is a subset of u and is still this neighborhood. And so that's all we're saying here, that this should be v sub x, but that because we have this open neighborhood of 0, c complement minus x, we can apply the previous corollary twice and construct this v sub x such that v sub x plus v sub x 4 times is a subset of c complement minus x. In general, so these are just going to be subspaces, or sorry, subsets. If 0 is inside of B, then A is naturally a subset of the direct product of A and B. And so we can go from this statement to this statement, right? Because this set is strictly smaller than this guy. Vx plus Vx plus Vx is inside of Vx plus Vx plus Vx plus Vx plus Vx. And so we can say this is true. And then we can shift both sides. We can add x to both sides. Because x is, again, just an element. It's not a set. It's just a single element. So we can shift both sides, and we can get this relationship. But of course, if this set is a subset of C complement, then of course it can't be in C, so the intersection is empty. And now, again, it's important to note that Vx, the only assumption for Vx right now is that it's symmetric. So we'll take a look at this next. Suppose towards a contradiction that this is not true, this intersection is not empty. Then that means there's vectors inside of Vx and an element inside of our closed set C such that this relationship is true, then we move V3 to either side. And the reason, again, why we can say that this is true is because Vx is symmetric, right? So this minus V3 is also in Vx. But of course, then this would imply that this is not empty, so that's a contradiction. So we've proven that this must be empty. Okay, next, we'll start by selecting an open cover of K. Then for each x in K, we pick one of these open sets, little k, such that x is inside the little k, and we'll rewrite it as x, as k sub x. Now, there might be, there will likely be, you can construct this open cover such that there's many little k's that'll contain a single x, but I'm saying pick a single one, right? Then we let w sub x be defined as k sub x minus x. Now, by definition, these k's are open, and we're just translating k, so w sub x is open, and it contains 0, so it's a neighborhood of 0. And so we, again, apply the previous corollary to say that we can find this v sub x, which is, of course, a neighborhood of 0. That's a subset of w sub x. And most importantly, the v sub x is symmetric. And then we can just shift v sub x back. We can add x to v sub x. And, of course, k is going to be a subset of the union of all these guys, right? Because v sub x contains 0, we're adding x, so we're basically just unioning over every element of k. This is still an open cover of k, right? We contain k, and these are all open sets, right? Because we started with open sets and we just kept translating them. Because k is compact, we can find a finite subcover. So this is where k being compact becomes useful. And of course, we'll use some indexing set A. So we'll say that we go over this finite indexing set A, and this will be a finite open cover of k. Okay, so now we let V be this intersection of all of these nice symmetric open sets V sub x. And the reason why it's important for K to be compact is because we can then get this finite number of V sub x's. And the reason why we want a finite number of V sub x's is that when we go to define V here, we want a finite intersection of these open sets, right? Because we're closed under a countable number of intersections of open sets, right? So V contains 0, firstly, right? Because all these V sub x's are neighborhoods of 0. So naturally, V contains 0 and V is open. So it's now an open neighborhood. It's redundant. It's just a neighborhood of 0. Pick some y inside of k plus v, then for some j and a, so for some index, we can say that y is of course equal to x sub j plus v1 plus v2. And we're saying that because we're going to be some element in k plus some element in v, and some element in k is just some x sub j plus some element in some particular v sub xj, plus some element inside of v. But of course, because v is an intersection of all such v sub xi's, we can just say that v sub 1 and v sub 2 are in the same v sub x sub j. So that's what we have over here. So then naturally y is inside of the union of all of these guys, right? And so it follows that because this was true for an arbitrary k, that k plus v must be a subset of this union.